Again, welcome to Profiler Internals. My name is Jakub, and I will be your speaker for the next 30 to 45 minutes. I have like 4 hours of content, so don't worry. Thanks to the sponsors, we have Chocolatey, Jane Street, Ironman Software, Knowledge Factory, and Synergy. And also thanks to all of you to be still interested in PowerShell coming to this conference, because this conference is the highlight of my year, always. So to address the speed up the code session or challenge, I didn't know about it, and they discussed on the stage, if you saw, to exclude me from it. But I think that wouldn't be fair, because I share all my knowledge with you in my talks, in this talk and in the other talk. I don't think this session will help very much with the challenge, unless you want to hack PowerShell, which they don't ban yet, I think. But there is a playlist called PowerShell Performance on my YouTube. The QR code is for that. It will also be on the next slide, so I can progress with my bio. And that might help, because there you can learn more about Profiler if you didn't already. So good luck. I will also try. But last time I got totally smashed in the shorten the code. My solution was like 2 times as long as the winning one, so I don't have big hopes. So this is me, Jakub. I work at Microsoft as a senior software engineer. Currently, I don't represent Microsoft here. That's left for some of the people from PowerShell team, so all opinions are mine. If you like my tools or your company likes my tools, please consider sponsoring my GitHub development on GitHub. So what is Profiler? Very short intro to it. It finds the slow PowerShell code automagically. And because we had this magic team in the morning, I want to see what the chief wizard Rob, or the more famous one from the story about the hobbits and the ring, has to say. You shall not be not fast. That doesn't really have a good ring to it, so maybe speed the fudge up. So this is the user experience of Profiler. If you use it, this is how you would learn it in 1 minute. You run trace script, you get this table from the self-duration, you look at the top 3 or 5 lines, and it tells you, here's how many % you will save by removing totally this line or optimizing it by 100%. So that's 91% of your code. This is how much it really takes, 164 milliseconds. This is where the code is, and this is what it does. So let's see that quickly in a demo. I have this write avocado PS1 that calls into a module, into a function, into whatever, just to write this avocado to the screen, this little emoji. It's not very impressive, but it's also very slow. It takes like 400, 500 milliseconds to happen. I can go through the code, I can find where is it slow, but why would I bother? I have Profiler. So I just run it through trace script, list the top 50 cell duration, and here I make the output a little smaller so you can see it. And it tells me here 75% of this code is being spent on invoke REST method. Because I'm using the stupidest approach to this problem, I call to server that has all the emojis, I ask it for avocado, get the glyph back, and then I print it to PowerShell command line. Surprisingly fast. It takes only 80 milliseconds to do it. Maybe I already have it cached somewhere. But this is the user experience. But how do we do that in PowerShell? How do we do it internally? That's for me the interesting part, because as much as I like this code, as I like this tool as well, I really liked developing it and coming up with ways to overcome the limitations of PowerShell and doing something that hasn't really been done before, apart from PS Profiler, right? But that takes a totally different approach. So my first inspiration was this set PS debug trace commandlet that is built into PowerShell and that writes to the screen what is currently happening in the script. It looks like this. We get tracing of all the calls. So we call the script, we import a module. For the module to be imported, it has to also export some members. Then we call into getIcon function. We enter the getIcon function that calls the getAvocado function. We enter that function and so on until we maybe reach this invoke REST method that we saw before, being on the top of the list that you get from Profiler, being the slowest call. And then we continue, we return, blah, 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 and we're done. So this already does a lot of the things that we would like to do. But to write a profiler, what do we need to do is that every time something happens, something interesting that we want to know about, we need to write down what happened and when it happened. What was the current time and what was the current operation. And then it's just a point of just processing that list of the things, and you have a profiler, and you're done. So in theory, it looks like this. We either do some kind of sampling. So every 1 millisecond, we look at what's currently executing inside of this process right now. And here I'm showing different operations in different colors. So here you can probably guess that the red one is the most expensive because it appears the most times on the stack trace. This is a good approach. We could use it, but we could lose some information if we don't hit the 1 millisecond with every call. So if we, for example, want exact hit count of a function, we can do a little better in PowerShell, because PowerShell is interpreted language on top of .NET, and we can plug into the right place, like where the trace line does its stuff, and just create some kind of events. So every time something happens, we write it down, we save the time, and then we just wait for the next event to come. And then this is our first event, then the next event happens, and the difference between those two is the time how much this first one took. And then we just repeat the same process over and over and over for every single code that runs. We write it down, we have a huge list, and we are very close to having a profiler. In theory, but how do we actually plug that into PowerShell? So that's the point of this whole talk. So first we need to find a way to hook a trigger. So here, if we look back into the output, you can notice this 4 pointy brackets pointing at the code. That was my starting point, how to find this code in PowerShell source base. So I went here to grep.app, which is a useful tool that indexes a lot of open source repos, and I search for that same string, and I can see very few items turned up in the PowerShell repo. Among them, this one, position.cs. I go there and I see it is inside of brief message. And so I can just use the navigation on GitHub to see where it's being used. That's very amazing. I go here inside of the debugger, inside of the method called traceLine, and I see write debug line. So that seems to have all the properties that we are looking for. We are tracing line through set psdebug trace. We are writing to debug, just how we do inside of the application. And so this would be a good place where we could plug in our trigger, where we could collect the information, collect what's being written to the screen, save the time, and write the profiler ourselves. And that was really my first approach to this. So I created a pull request to PowerShell, just adding a collection and collecting all of that information inside. We can see it here inside of debugger. I placed it a little more above in the call stack than the trace line. I put it above the call to the trace line, not inside of the trace line, because there I have the function context, and that has way more information about what's currently being executed. This pull request, sadly, was never merged because there were a lot of ideas how to do this better, how to plug it in, how to make it more reusable. Perfect kind of become the enemy of the good enough. And so this wasn't merged and it never got into PowerShell 7. And it was for the good because I also wanted it for PowerShell 5. And there was no chance in the world that this would be inside of PowerShell 5. So I had to come up with different approaches. So my second approach was this Harmony plugin, which it's a DLL that you download for .NET, and it enables you to replace any static call inside of the process with anything that you want. So I just used it to replace the traceLine call, and it worked beautifully in PowerShell 7. Not in PowerShell 5. There I got a lot of weird edge cases, like you start the session, it doesn't work, you start the session again, it works. It was very unreliable, but it was a start. But then I thought, well, we are writing to the screen. I already write a PowerShell host, so maybe I could somehow patch the call to writing to the UI. So if we go back to my VS Code, I wanted to replace this call to write PSDebug with something that I control and where I can plug in my own callback. And so how do I even start debugging this? Very easy, PowerShell is .NET, so I can just go here, start a new process. I will just ask it what the PID is. We'll start PowerShell. We can close this one, we will get there. Say, attached to a process, the latest one is always on the top. They sometimes break it, but I always report it to put it back because I use it every single day. And then I can create a breakpoint. Visual Studio has this function breakpoint functionality, so I just create a new breakpoint, say trace line, I already have it here. And we're attached to the process, so now I just need to do set psdebug trace1 and say hello. And we are entering that code. We ended up in trace line. That's what I shown before. We have the extent of the script, which is what is going to be executed, and it says hello. So we are really in the right process, in the right place. But if we then navigate in this place, we have this write debug line, and you can notice that it gets just a message, just a string. And that's not really that much information that we get, because there's a lot of information on the script block, which is this one, iScript extend, but not really that much information about just the message, because that just tells us where we are in the script. But anyway, I continued, and I thought maybe I can use this. Maybe I can just collect this information, write it down, and then make something out of it. So if I try this, this is what I want to have. I want to have the whole AST of the script block. I want to have the location. I want to have which module it's coming from, currently none. I want to know where I am on the call stack so I can see if we are recursing or not recursing, and so on. So I want to patch the UI to replace it with my own tracer. How do I do that? From my previous experience with PowerShell, I know that the UI is being kind of hidden here. So we have this host.ui, and there I can plug something myself that will replace how we write to the screen. And I want to replace it with something that will just replace how we write to debug, but I don't want to touch anything else. So I implemented that here in the tracer host UI inside of Profiler. And it's implemented through this PS host user interface. How I got to this whole conclusion? Well, let's see. We have this host UI. We can look at the type. That's internal host user interface. We can look at which assembly it is in, what is the location, and then we can open it. In my system, I just have DLLs assigned to ILSpy, which is a tool that's a decompiler. So we see it open right here. We can look at this internal host user interface. We find that type. It's internal. And we can look through all of the code to quickly realize that it always offloads to this external UI field, which we have right here. Come on, go away. And that's being implemented by PS host user interface. PS host user interface is a public type that you can grab and that you can implement yourself. And that's exactly what I did here in the code. So I implement it. I have this tracer host UI. I give it the UI that's currently being used, so I can forward one more time to it. Except for that single case where we are writing to the debug line. So that's this call. If we don't have any tracer, tracer is a thing that saves the data for us or processes the data for us, then we just write to debug line. if we do have it, then we offload to the tracer and we don't write to the debug line. So this gives me a trigger where I can say something interesting happened right now, something interesting happened right now, and save it. But it doesn't give me any access to any additional information about the execution because I only have the message. So I continue digging. Ideally, I want to be above this call, right? I'm somewhere inside of here. So maybe we can navigate there with a bit of luck. So this is where I would be plugging in my tracer, but I want to be somewhere here above because that's where I get the function context, and function context has all the information that I need. Unfortunately, this is not PowerShell. In PowerShell, you can inherit the variables down into the functions, but in C# that doesn't work. C# just doesn't work like this, so I cannot just say function context in here inside of write debug line. I need to somehow get to this place where I have the function context. But luckily, I can look at that. Here I'm pressing Shift F9 to look at this window. And I can notice that I have a execution context. That sounds like a very familiar name. And on the execution context, I have a debugger. And debugger has all the information about the current execution. So it should have the function context. If we can find it, _f something. No, it's actually here in the call stack list. And it has the current code that we are executing. We are on top and we are saying this hello. And because it's a debugger, it has all the other interesting information that I'm interested in. So execution context. Who knows about the automatic variable called $execution context? Probably almost everyone, right? So we have that here in PowerShell. So execution context. We can look at the type, which isn't execution context, but it's engine intrinsics. And if we look inside of this, we get something that's called context, a field on this that has the execution context, and there we have all the information. So all we need to now figure out is how do we access this internal state, and that's very easy because this is .NET, so we can use just reflection and look at that code. So where do I do all of that? I go back to Profiler, push all the information in. So I give it execution context, go away. I give it host UI. This is my setup code where I'm setting everything up to be able to patch the current session, replace the UI, give it the other context, dig into the debugger, and start saving all of that information. And then inside of Profiler, in my C# code, I have this patch method which receives the context, receives the UI, and receives a tracer, something that will be saving information. And then here I have a bunch of reflections. So first I need to look up the external UI thing that we saw on the internal host that we want to patch. The name is different between PowerShell versions, but that's about it. I save that, and that gives me access to the current UI, so I can forward to it. Then we get the context, which is the internal context field on the execution context variable that we passed in. That gives us the access to the debugger. Debugger has the current call stack. On that, we are interested in two things. One, how big it currently is, because from that we can tell we went into a function, we went outside of a function, or we stayed in the same function. This is important for tracking recursion and tracking function calls. And it also has the function context, which has all the information about the current code, where it is, in which file, and what is currently being executed. So we get that by calling this last function context on the call stack, and that will give us the function context. And from that, we can collect all of this interesting information, like what's the function name, what is the execution context, what is the script block, where we are in it, and so on. So we have a trigger that we can call every single time something interesting happens. And now we have a tie-in to the debugger where we can collect all the interesting information that we care about. And getting time, knowing when what is the time? It's very easy. We just ask the operating system by calling datetime UTC time or stopwatch current timestamp. If you know something about reflection, you might think this is very slow, and it is. But luckily, we don't have to do it every single time we're tracing something, because profilers need to be as little impactful on your code as they can. And so here we call all the kind of callbacks to the functions. We save them in here, and then we invoke them. So it's as fast as calling a normal method inside of C# rather than doing this reflection lookup every single time we trace. And this is what happens every time any line of code is being executed in a trace line or trace script session inside of Profiler. So this gives me point where I have a trigger hooked. I could be able to collect all of this information. I can plug in any whatever callback I want to be processing this information and saving it into a list. And this is where we get all the information through the reflection. So how deep we are in the call stack, what we are recursing, which function is being called, and so on. So we can then post-process the data. I see I jumped a lot over my slides. And so now we are in this place. We have a trigger time, all the details of the code that we need. So now we go to the tracing. And tracing in Profiler is isolated under iTracer interface because we have two different implementation. One is for Profiler and the other one is for Pester. So both of those use the same kind of core, what we saw until now, how we patch the UI, how we get the information, how we send it to this tracer, but then each of them is processing the data differently. The Profiler one collects everything in memory and then processes at the end. The code coverage one just looks at, this is the code you called. If you called it at least once, I don't care about it. Tell it to me 2,000 more times. I already have it in my hash table, so I will just return. And so that's being implemented here in the Profiler tracer for the Profiler. We save all the info into a list. We try to a little bit optimize the memory space by using struct, so we don't have the header in the C# class. And if you look at this class, how it's being implemented, it's pretty simple. This is the callback. This is the information we pass in. And then we just save a bunch of information. What's the current time? What's the timestamp? What's the memory currently being consumed? How many bytes of memory we allocated? What is the index on the list? What is the script block, and so on and so on. And then we create one object from it, assign it to the list, and we are done. We're just trying to collect everything into one big list of events. One thing that in the middle saved me lots and lots of time, and that's still there, is index on every single item into this list. Because if we have a list and then we want to go from this part to this part, or we want to link two things together, how do we do that? If we have an index, it's very simple. We just add a field to the item and we say, do you want to know where the return from this function is? It's on the index in this list, that's 1744, and you are at index 1. And this is being used in many, many places because we need to trace how we enter the function, how we leave the function, where we are returning, and so on. So this is very primitive, but it turns out to be extremely useful thing to do, to put the index of the item in the actual list. Then we have just the timestamp. So how we figure out the time from it, we just take this timestamp and we subtract it from the next one. The arrows seem to be a little shifted, which is wrong, but this one goes here and this one goes here, and those are supposed to be milliseconds. So the difference here is 1001, and that's the duration of this start sleep for 1 second, which I hope makes sense. Then we're also tracking how deep we are in the function calls. And this is important for recursion and also for try catches. So if you call code like this, you have function B that calls function A, and then function A throws an exception, you will not go back into B and back into A. You will jump all the way up into this try catch, and you need to keep track of that. Because if you don't, then you will start accounting time incorrectly, and you will not get the correct results in the end. Let's see if I have a demo for that. Actually, I don't. That's good. And then there's more complications where we are using the index. So every single item has an index in this event list. And then we have the caller index, which is who called me, so I can go back to him. And then we have the return index. Where am I returning from this function? For a normal function, it's pretty easy. You enter it, you calculate, am I still deeper in the call stack than until now? Well, it's for all the functions. You enter the function, you take note of how deep I am. So that's this level. I'm on 1. Then I go deeper into the call stack, and then it throws and it jumps back to 1. So all of those previous things had to return on this index. So this is where I'm returning. They are returning on 7. This way we can link together the executions, and we can link together the jumps, and we can link together the recursion and actually make sense of it. If the index wasn't there, then it would be all just references to this method thing, to this method thing, and it would be so complicated to track. This way, it's actually quite easy to understand, at least for me when I draw it down like this. This is all written down in this process flow, which is, I think, very nicely annotated and documented. So if you want to see how this is being done in the real code, then I welcome you to navigate to this one and read all the code for yourself. And then we just need to summarize the data. From this long list, we need to put together the lines that you see in the code, because Profiler is focusing on showing you the most expensive line of code that you have. It doesn't tell you this one single call took this much and this one single call took this much. No, it shows you the line. It aggregates all the data to that line. And that's done here in process lines. What we do here is that we create a map of the lines of the code inside of a file. We then aggregate the data based on when we entered the function and when we left it. And then we put together those durations or those self-durations, and then we just list it inside of Profiler. So this gives me overview of every single line, how many times I saw it being executed, how long did it took, and it has a special case for recursion because that needs to be addressed. Otherwise, it gives you wrong results. So for example, here we have an example of a recursive function. My original approach was just find call dog in every single place, add it together, that says 400 milliseconds, which is wrong because this whole thing, if we actually measure it, only took 100 or 101 milliseconds. So let's jump to code and let's see that. So here I have this hello function. We enter it 50 times and we start sleep milliseconds 15. And then again, we recurse into the function until we reach this break. And so in my original approach that was quickly reported by someone, I tried to do something like this. Take all the traced events, aggregate them. Well, find the ones that starts with hello, so that's this function call, and aggregate them together, because that's obviously in my head how long it should take. But then we get a result like this. You took 23.5 seconds to run this single function, but the whole script finished in less than a second. Just tiny bit wrong. Another bug was in relation to Linux, where the milliseconds don't always have the same amount of splits. So you could have like 88,000 milliseconds inside of a second. So that also broke everything, but that was more easy to fix. So the correct approach is we have the events. We find, for example, the first one, And then we look at its return index, where we are returning. So rather than doing this, we are looking at this, and then we look at where we return, and then we take the difference. And that shows us this number below, which is correct, 885 milliseconds and a tiny bit. And then the whole script took just a tiny bit longer than the whole thing. So that's one thing, averted. And then we just need to create the final view. So you can go to your trace and you can say top 50 self-duration, the most useful thing we have in Profiler. And that's all done in PowerShell and is quite easy. Here's the implementation. So we take the all. All is the summarized lines because it's all lines. We look for self-duration that's greater than 0, just an optimization for the ordering. And then we order it by self-duration in descending, select the first 50. We apply this view, so then you can use the format table and it automatically shows you the important things first. And then it just writes to the screen how long this took. So in the pinkish output, you can see how long this took. And that's the whole implementation of Profiler. Very easy. I encourage you to replicate this for yourself and maybe use some of those things that you saw, how to plug into PowerShell to a little bit break the challenge tomorrow. And so mostly what I wanted to show is that I really enjoyed this tool, how to write it and overcoming the things that were put in my way. So don't get discouraged when things don't go your way. Dig deep. You might learn a lot of stuff. I know that I learned a lot of stuff about how PowerShell works, how to debug it, how to plug in stuff, how to do reflection and so on. And mostly I had a lot of fun doing this. So yeah, that's it. Right on time. Well, almost. So Q&A if there are any questions. I have one more demo that will, well, not blow your mind, but it's interesting. Do we have any questions? You will have to shout. This is Justin, right?
Yeah. How's the speed scope stuff work?
How does the speed scope stuff work? So speed scope is an export for like a JSON format that you can export, and it gives you this flame graph on speedscope.net website. It is just another summary, just another view on the data that we have. I use the function view that we have because without it, there was too much information for the speed scope to make it useful. So right now, how it works is more as if you look at the top 50 duration, where you kind of get the overview of this is the big things that you need to address, but the details are a little hidden. But mostly I would encourage using the top 50 self-duration for most investigations. But yeah, it's just a view. There you go.
Is Profiler finished, or do you imagine other new functionalities? What is the roadmap, the coming roadmap?
Yeah, so question is if Profiler is finished. I think it was finished way before I myself realized it's finished, because as I use it more and more, the most useful view is the top 50 self-duration. That's what I use in most performance investigations that I look at. I just run a script, look at the top 5 lines, and that's it. But there is a lot of other hidden functionality, like you have the event list, you have call stacks, you have memory views, you have function views, you have per module stuff, you have the speed scope that Justin was mentioning. All of those things are kind of extra that I think it's just me using for some things. But if I release the first version with just the top 50 self-duration view, I think that would already be useful for 99% of users. I don't currently have any timeline or any expectation to add new functionality, but if you propose it in the issues or implement it yourself, I will be happy to review your code and get it merged. Please?
Is
according to yours, or do you like push this project with Microsoft since you're hired?
It is. The question is if it's a personal project or Microsoft project. It is my personal project, same as Pester. I don't get Microsoft backing on either of those.
The reason for my question would be they were talking about this NAR repository this morning. Will Pester or Profiler be published on this repository, or will they stay on the gallery?
You were talking about MAR repository, if it will stay on gallery or if it will be moved there. I don't know what it is, but I assume that's like a Microsoft central repository for tools. Is that right? So if that's it, then unless they decide to buy it or they open it for open source projects to be inserted in there, then I don't see Profiler or Pester becoming part of that. But also, Pester was already part of Windows, so maybe it will happen somehow. Oh, Jordan?
Have you encountered any breakages in the API? So I know you're doing reflection across the PowerShell versions. Has there been any big changes that you've had to deal with?
No, I haven't really seen any breaking changes. Question was if there were any breaking changes in the API that I'm reaching into through the reflection, and I didn't see any changes. We are accessing maybe 2 or 3 fields. The things changed between PowerShell version 5 and 7, but since then they didn't really change at all. Hopefully it would be easy to patch anyway. Do we have some more? Ah, okay. So I still have like 5 minutes. That's good. So I said that Pester and Profiler use the same core, but if you look at Pester, it doesn't have any dependency on Profiler, and the other way around, of course. And so how do we do this? If we navigate to this implementation for the tracer, which is the thing that patches the UI and I collect the information and push it into the iTracer, then here we can see, well, we have some compiler directives because sometimes we compile it for Pester, sometimes we compile it for Profiler. We also have a script that copies all of this code into the Pester repo, and we set this compile time variable to be able to give it a different namespace. So in reality, we have 2 totally, completely different versions of the Profiler core in each of those things. But in some cases, like when we are trying to profile Pester, we want to be able to use the core for both of those things. Like if I want to profile the code coverage that's inside of Pester, I want to be able to use one of my tracers plus the other one. But if I activated both profilers at the same time, one would disable the other. So the solution to that was that we have 2 kind of slots for the tracer, for the thing that saves the information. And whichever big tracer patches the UI first stays. So in the case where we have Profiler profiling Pester that's doing code coverage, we register the one for Profiler. In the first slot, in tracer 1, we register the tracer for Profiler, so the Profiler tracer. And then when Pester starts, it detects, is the big profiler implemented, just by looking at if there is a type existing that's called Profiler. And if it does, then it registers and it inserts inside of this other slot. That sounds simple enough, but I said we have 2 completely different implementations, and this is C#. So by having an iTracer in one assembly and iTracer in other assembly, for .NET, they are totally different things because .NET doesn't do duck typing in most cases. And so we need to take this shape and mash it into this other shape somehow so we can call it, because they are not the same, not at all. I will show you the implementations, I guess, to make it a little more obvious. So here we have code coverage tracer inside of Pester tracing. And this name for the runtime for .NET is absolutely different from, where are we? Tracer, tracer, tracer. Oh no. This is a wrong link, is it? Profiler tracer. Yeah, there we go. So this name, also iTracer, but totally different thing than the other iTracer. They are the same code, they're just compiled into a different DLL, so they cannot collaborate. So what we have is this external tracer adapter, which does more reflection magic, and is the reason why the iTracer implementation, which we have here, or the other copy in Pester, only uses those types that already exist inside of PowerShell. So we have string, iScript extend, script block, integer, string, and string. Because then what we can do is that we have this adapter, we receive the iTracer implementation, we look at it, and we think, is there a method called trace on whatever this object is? If yes, and it has those parameters, then we assume it's some kind of tracer that can trace, even if it's coming from Pester, even if it's coming from your implementation, we don't care. It has the correct shape, and that's the kind of definition of duck typing. If it looks like a duck and quacks like a duck, it's a duck. But in our case, it's a different tracer. So we grab that. We have also opportunity to do some backwards compatibility. Like if we implemented one version that takes 5 parameters and another one that takes 4 parameters or more, we can detect all of this here. We get the method callback, and then when we need to trace, we just give it the data right here, and we invoke the method that we just grabbed. And by this, we kind of bridged the gap. So we are able to use an implementation of iTracer that is not the iTracer that the other side expects, doing duck typing for our tool, and not having any dependencies in between those two, but being able to communicate. So that's the final demo. If there's one more question, I would be happy to take it. If not, please talk to me in the corridor, maybe if you're too shy to ask it, or if you think about it afterwards. Okay, no questions. So thank you very much. Thank you very much for listening.